Welcome back to the deep dive. Today, we're looking at something that, honestly, it feels a little bit like a heist movie.
A heist movie.
Yeah, but instead of stealing, gold bars or diamonds, we're talking about stealing or maybe reclaiming the ability to build civilization itself. We're digging into a concept the source material calls the recursive loop.
Right, the recursive loop. And it does sound dramatic, doesn't it?
Yeah.
But I mean, when you really look at the economics of manufacturing, it is dramatic. It's probably the biggest economic trap in the modern world.
Okay, so let's set the scene for everyone. The basic idea is that to build high-precision tools, you need other high-precision tools.
It's the ultimate chicken and egg problem.
Exactly. If I want to build, I don't know, a tractor or a medical device, I can't just hammer it out in my garage.
Nope.
I need machines that are incredibly accurate. And to get those machines...
You have to go to the legacy economy. You have to pay the gatekeepers.
Yeah.
And that's the trap. The whole industrial model is set up to make high-precision manufacturing a scarce, incredibly expensive asset.
So you're talking hundreds of thousands, maybe millions of dollars, just to get in the door.
Just to get started. You need the machine to make the machine, and they own that first machine.
Which brings us to today's topic. We are unpacking the machines of abundance. The sources call this a prison break from that whole racket.
Yeah, and the goal is this thing called capability closure.
Capability closure. I love that term. What does it mean?
It basically means a community, or a factory, reaching a point where it can produce absolutely everything it needs to sustain and expand itself, all without relying on an external supply chain.
So, civilization scale independence.
That's it.
And the methodology to get there. This sounds like it's straight out of science fiction, G-Boppo.
Yeah. The generalized industrial bootstrap optimization problem. It's a mouthful.
It sounds like a robot from the Jetsons.
It does, but think of it less like a robot and more like a strategy guide for a video game. You know, like in Civilization where you have a tech tree.
Sure, yeah. You have to unlock pottery before you can get granaries.
Exactly. GBOP is an algorithm that looks at the entire universe of industrial tools. Everything from a screwdriver to its semiconductor plant. And it calculates the absolute minimum seed set you need to buy to break that recursive loop.
So it's asking, what are the key pieces of tech I have to buy so I can then build everything else myself?
Precisely. It identifies the pivot points. Once you have that seed set, you stop being a consumer of industrial gear and you start being a producer of it.
Okay, so let's be clear. We're not talking about someone buying a drill press for their basement.
No, not for making birdhouses. We are looking at a consolidated tool chain. The sources call it a secessionist factory.
A secessionist factory.
And the mindset shift is the key part. You're not just setting up a shop to make parts for someone else. You're building a facility where manufacturing becomes a background utility.
Something that just happens cheaply and easily.
Right. So you can focus on the actual products, not the process.
Yeah. Okay, let's get into the seed set. The sources highlight 2 key machines and a huge assembly system. Let's start with the workhorse. They call it Machine A.
Machine A is your daily driver. It's a 5-axis precision workhorse. If you're looking for a comparison, think of something like the Tormac 1500 MX, a really capable piece of kit.
But it's not just a clone, right? The sources make a really big deal about the frame. They're using something called epoxy granite.
Yeah.
Now, when I think of big machinery, I think of cast iron. Big, heavy, gray metal. Why the switch?
This is a massive differentiator.
Yeah.
Cast iron's been the standard for a century because it's heavy, it's relatively cheap, but it has a major flaw. Think of a big church bell.
Okay.
It's basically a big piece of cast iron or bronze. You hit it, what happens?
It rings. It vibrates for a long, long time.
Exactly, it resonates. In machining, that vibration is called chatter, and chatter is the enemy. It ruins your surface finish, it breaks your cutting tools, it limits how fast you can cut.
So if your machine is vibrating, your accuracy is just gone.
Out the window. Now, epoxy granite is a composite, it's granite aggregate mixed with epoxy. It has 10 times the vibration damping of cast iron.
10 times.
10 times. You hit a block of it with a hammer, doesn't go B-O-N-G, it just goes thud. It absorbs the energy instantly.
So what does that mean in practice? Chatter-free cuts.
Chatter-free cuts, way better surface finishes. But here's the kicker for the economics of it. The sources cite a 30% increase in tool life.
Wait, 30% just from changing the frame material?
Yes, that constant vibration creates microfractures in the cutting edges of your tools. You get rid of the vibration, your expensive carbide tools last 30% longer, your operating costs just plummet.
That's huge. Okay, the other tech detail that jumped out at me was the 23-bit absolute encoders. Now, encoder sounds like jargon, but the benefit seemed really practical. It reminded me of my old printer.
Oh, the whir click whir dance every time you turn it on.
Exactly. It had to slide the print all the way left, hit the wall, then all the way right just to figure out where it was.
That is precisely what most CNC machines do. It's called a referencing sequence. The computer has no idea where the motors are when you first power it up, so it has to slowly crawl to its limits to find zero.
So waste of time. And if you lose power mid-cut, you're in trouble.
You have to start the whole dance over. But with the 23-bit absolute encoder, the machine knows its exact location in space the instant you turn it on. No referencing. Power on, ready to cut.
Okay, so it's stiffer, faster, smarter, but here is where it gets really interesting, and honestly, a little hard to believe. The price. If I go buy a legacy machine with these specs tool changer, mist collector, all of it, what am I paying?
You are looking at around $42,000, a significant barrier to entry. That's a new car.
But the sources claim this vertical integration strategy just collapses that cost. They say you can build this thing for between $8,000 and $14,000.
They do.
Okay, hold on. How? I mean, really, how? You don't just shave $30,000 off the price. Are they using cheap parts? Is it held together with duct tape?
No, and this is the part that trips people up. The savings come from stripping away what you could call the legacy tax.
A legacy tax.
When you buy that $42,000 machine, you're not just paying for metal and motors. You're paying for the brand's marketing, the dealership network, the shipping for 3,000 pounds of iron across an ocean.
Okay, I get that, but the source says you're making your own spindles, your own motors. That sounds insanely difficult for a small shop.
It used to be. 10 years ago, you couldn't do it. But now, you can buy high-grade neodymium magnets as a commodity. You can 3D print the molds for your own coil windings. The tech has advanced so much that a skilled person can build a spindle that rivals a commercial one for a tiny fraction of the price.
So you're trading your labor and your knowledge for the massive markup a corporation would normally charge.
That's it. You are paying for raw materials and electrons, not for overhead and CEO bonuses. That is how you get to $8,000.
That takes it from, I need a major business loan, to I could maybe put this on a credit card.
Right. But that's just the appetizer.
Yeah.
The main course is what happens to your operating costs once you have the machine.
This was the part of the research I had to read twice. The source calls it an economic phase transition.
And it is the perfect term for it.
So the claim is that the utility rate, the total cost to run this machine, is about 27 cents an hour.
Correct. 27 cents.
Come on, I can't park my car for 27 cents an hour. How is it possible to run a high-precision industrial machine for less than a gumball?
I know it sounds crazy, but let's walk through the math. First, you assume you manufacture it yourself for the low-end cost, so about $5,000 at scale.
Okay, $5,000 initial investment.
An industrial machine like this has an operational life of about 40,000 hours before a major rebuild.
40,000 hours. That's years of nonstop work.
So you divide $5,000 by 40,000 hours. The depreciation cost, the machine using itself up, is 12.5 cents per hour.
Okay, that math checks out. But what about power?
Modern servo motors are super efficient. And if you have decent industrial rates or solar, you're adding maybe a dime. Add a few more pennies for the wear on the cutting bit, you total it all up, and you land right around 27 cents.
So because you didn't pay 42 grand up front, the mortgage on the machine is basically zero?
Exactly. And think about what that means. At 27 cents an hour, the machining cost becomes irrelevant. The cost of manufacturing literally drops below the cost of the raw material you're cutting.
And that's the flip. Normally, if I want a custom gear, the metal costs $5, but the shop charges me $100 because of their machine time.
Right. But in this new model, the metal is $5 and the machine time is 50 cents. The transformation is almost free. Industrial capacity is no longer a scarce capital asset.
It becomes a utility.
It becomes as accessible as tap water or electricity.
That really is a phase transition. The question changes from, can I afford to make this, to simply, do I have a good idea?
Exactly. But we can't build a whole civilization with just 5-axis mills. They're great for smaller, precise parts. Sometimes you need a much bigger hammer.
Let's talk about machine B, the industrial hammer.
A high capability, 9-axis mill turn.
Okay, 5 axes I get XYZ and 2 rotations. But 9 axes? That sounds like we're opening a portal to another dimension. What does a 9-axis machine even look like?
It is a beast. For comparison, in the legacy market, this replaces machines like a Mossack Integrex or a DMG Mori NTX. These are the absolute Ferraris of the machine tool world.
So what can it do that the 5-axis can't?
Think about making a really complex part, like a hip implant or a turbine blade. In a normal shop, you'd put it in a lathe to turn it, then take it out, put it in a mill to drill holes, flip it over, put it back in.
And every time you move it, you're risking an error, a misalignment.
And you're paying a human to do it. A 9-axis mill turn does everything at once. It has 2 turning spindles, like 2 hands, and a full milling head that can approach from any angle.
So it can pass the part from one hand to the other without ever letting go.
That's a great way to put it. This is what the source calls the one-and-done concept. Raw material goes in one end. A completely finished, complex part comes out the other. No human touches it.
That sounds incredibly efficient, but also incredibly expensive.
In the legacy market, oh, absolutely. Yeah. You're looking at over $1.3 million for a top-tier machine. Only massive aerospace or medical companies can even think about buying one.
But again, the Secessionist factory has another plan.
By building it in-house, using all the same principles, the epoxy granite, the custom spindles, the commodity sensors, that cost drops to between $150,000 and $250,000.
It's still a lot of money, but it's not $1.3 million.
It's a total game changer.
Yeah.
It means for the price of one legacy machine, you can build 5 or 6 of them, you get redundancy, you get scale.
Okay, so we've got the small precision parts covered, gears, motors, medical tools, but we're talking about building a civilization. We need buildings, vehicle frames, big stuff. You can't fit a house in a milling machine.
No, you can't. This is where we have to scale up from the grain of rice scale to the dinosaur scale. And for that, we have the robotic assembly cube.
This thing sounds both terrifying and amazing. The notes call it a 40 by 40 by 40 foot universal frame printer. That's the size of a small building itself.
It is. It's a massive gantry system. But the most poetic thing about it is the recursive logic. The cube is designed to be built using the exact same 2-inch steel tubing it's designed to assemble.
So the machine builds itself.
In a sense, yeah. If you want to expand your factory, the cube can cut and weld the parts to build another cube.
I want you to paint a picture for us. What's it like inside the cube when it's working?
Okay, picture a large, open cubic frame. Inside, hanging from the top rails, you have 8 collaborative robotic arms. They move on a triangulation system, kind of like a spider cam at a football game, but rigid.
And they're all working together.
It's a choreography. It's mostly silent except for the hiss of the welders. 3 arms will swoop down, grab a long piece of steel tubing, and hold it perfectly in 3D space. They become the hands.
So you don't need clamps or fixtures or guys with tape measures?
None. The robots are the fixture. They hold the steel in midair at the precise angle. Then 2 other arms, the welders, move in, strike an arc, weld the joint, and move on. It's fluid, it's continuous.
Wait, how do the robots know which way to hold the tube? I mean, a steel tube is just a steel tube. It doesn't have a "this end up" sticker on it.
Oh, this is the genius of the pipeline that feeds the cube. You can't just throw raw steel at it. You need what the source calls smart tube technology.
This involves those 2 smaller machines, right?
Correct. Before a tube ever gets to the cube, it goes through a preparation machine. It cuts the tube to length, notches it. But here's the key part. It uses a laser diode to etch orientation barcodes directly onto the steel.
Barcodes? On the steel itself, like at the grocery store.
Exactly. Every single piece is tagged with a unique ID and orientation data.
So when the robot arm picks it up,
it scans the code. It knows this is part number 450, rotate 30 degrees clockwise, present to this coordinate.
And there's a bending machine, too.
Yes. If the design needs curves, a bending machine reads that same barcode and hydraulically bends the tube to the exact angle. So the parts arrive at the cube, pre-cut, pre-bent, and digitally tagged. They are self-jigging.
Self-jigging. Why is that term so important?
Because in traditional heavy manufacturing, jigs are the hidden killer of innovation. If you want to build a car chassis, you first have to build a massive custom steel frame to hold all the pieces. That jig costs a fortune.
And if you want to change the car's design,
you scrap the jig. You build a new one, it frees you in place.
Yeah.
But with the cube, the robots are the jig. You want a new design, you just change the software code. The robots move their arms to a new position. 0 retooling cost.
That is incredibly flexible.
The sources say this drops the cost of large-scale frame assembly to 1/10 of industry standards. You could print a warehouse frame, then a tractor chassis, then a bridge section, all on the same day.
That's a lot to take in. We've gone from one mill on a block of epoxy granite to a self-replicating factory that can print buildings.
And that is the whole point of the machines of abundance. It's not one cool gadget, it is the entire ecosystem.
So let's zoom out. What does this all mean? When we look at these three systems, machine A, machine B, and the cube all working together, what have we actually built?
We are looking at the dematerialization of cost. We're moving from a world where you need millions of dollars and permission from a dozen corporations to start a factory to a world where high-precision manufacturing is, as the source puts it, neutral as the air we breathe.
It just changes the power dynamic completely. It feels like what the internet did for publishing.
That is a perfect analogy. Before the internet, if you wanted to publish a book, you needed a printing press, a distribution network. Now you just hit publish. These machines do the same thing for physical objects.
Capability closure.
Capability closure. When you own the means of production, I mean, really own them, from the source code to the motors, you achieve independence. You are no longer held hostage by the legacy economy. You've broken out of the loop.
But this raises a huge question for the future, doesn't it?
It absolutely does.
If industrial capacity becomes a near-free background utility, if making stuff costs 27 cents an hour, what happens to the idea of value when we are so used to paying for the physical thing?
But if the physical thing is cheap to print, the value has to shift. It shifts entirely to the idea, the design, the code, the creativity.
So we stop valuing the plastic and the metal, and we start valuing the solution to the problem.
That's it. It's a provocative thought. In a world of abundant manufacturing, the only real scarcity left is human ingenuity. If you can build anything for pennies, what will you build?
That is the question. We've got a lot more to cover in this series, but for now, I just want everyone listening to imagine that. The barrier to entry is gone. What exists in your head that you would finally put out into the world?
I think we would see some incredible things.
I think you're right. Thanks for listening to this deep dive. We'll see you next time.